So let us now go through the method overview of a typical TLC process. A typical or a general method of TLC involves the preparation of the sample. So typically, again, most of our analytes of interest will be in a complex matrix. It may be a plant, it may be animal cell, it may be serum or plasma. So the sample preparation usually involves extracting these analytes of interest or the bulk of it from your matrix. Then the second step, which is important, is the plate preparation or the selection of the kind of plate you want to use. Now, again, at the time that Ismailov and Schreiber and Kirschner were working, plates were being made in the lab. And even now, students starting out, say, for just standardizing it or in the lab, do prepare plates, but increasingly very well standardized commercial plates are available with a wide range of selection of stationary phases depending upon the type of compound that you're wanting to separate. The next step is the sample application and separation. And typically, right after your tank, as we saw, the sample tank in which your plate will go in for the separation, has achieved the atmosphere is in equilibrium with the solvent, the separation, the plate on which the separation will occur is placed in the tank. So the tank with the solvent system is a critical component of the application and separation process. Next comes the visualization of the compounds in your mixture. Now this particular step is critical because you will have some idea of whether the separation will took place or not, of the components of your mixture, and it will also give an indication of whether that separation happened in the optimum fashion that the scientist had visualized. And if the process of TLC was done for, say, a preparative purpose, then these spots that have been visualized and often marked out with a pencil can be eluted for further analysis. So to give an example, when we are trying to separate different components of a molecule such as the high-density lipoprotein, we typically first do a TLC separation to separate the phospholipids from the cholesterol, etc. And then those phospholipids are eluted out and the fatty acid composition of the phospholipids then can be further analyzed by gas chromatography. So to analyze the different, the fatty acid components of the different kinds of lipids that are present in HDL, TLC is the first step, which then subsequently is combined with another chromatographic process to get the a more accurate picture of the individual fatty acid composition. Now this is the method development overview which we just discussed in the previous slide, but with some more specifics. So selection of the stationary phase is critical, selection of the vapor phase and the solvents is critical, and then once the range of solvents that would be required for the expected analytes that are to be separated has been decided, then the composition of the mobile phase has to be optimized. Then the selection of development mode has to be optimized. One of the considerations for the kind of development mode that will be used is, of course, whether it is needed for subsequent analysis or whether just a semi-quantitative or a qualitative estimate is required or whether a quantitative estimate is required. And then the selection of other operating parameters, especially if, say, this is functioning in a high performance mode, so other operating parameters for, say, an automated setup may come into play. Now, one of the methods that I used, or rather one of the algorithms that has been used for many decades now, is called the PRISMA. PRISMA is a statistical geometric way of optimizing the strength of solvent and the selectivity of the mobile phase so that the best combination can be achieved for the best separation of the analytes in the mixture. Now we have, as we discussed, the first step after the extract of your interest has been prepared is the stationary phase, and support on which the stationary phase will be coated in a TLC experiment. So the commonly used backing, which is on which the stationary phase is put or layered, is often either glass, aluminium or plastic, and each of these supports or the backing materials have their advantages and disadvantages. So glass, for example, is chemically inert, but it is brittle. Aluminium is not very good if it's strongly acidic or oxidizing. Stains are being used for development. And plastic is poorly heat resistant, which basically means that if your development process, for example, involves heating your stationary phase so that that some reaction will take place in the analytes that have been separated for them to be visualized, then plastic may not be a good support or a backing to use. However, now even for plastic, there are high heat resistant plastics being designed, but if possible, the commonly and more easily available glass and aluminium supports are used in case a heat step is required. Now here again, before we get into the specifics of some of the examples of stationary phases and development methods, remember that depending upon the relative polarity of the stationary phase with respect to the mobile phase, the chromatography may be called either normal phase or reverse phase, and I shall discuss later. Now, this is an overview of plate preparation. I basically said that nowadays a lot of these plates that are available are commercially available and very well standardized, but labs still like to prepare their own plates. It will be cheaper. Maybe you can play around a little bit with the compositions of your stationary phase. So a typical process, a typical plate preparation process involves an adsorbent material which will act as the stationary phase, which will be used for coating. And as we discussed, commonly used stationary phase involves either silica or modified silica, then a kieselguhr and alumina, which is aluminum oxide. Then using this absorbent material, a slurry is prepared. And this slurry basically involves mixing the adsorbent material, which will be your stationary phase, with a binder, which is typically calcium sulfate as gypsum, and water. Now, this binder will help the stability of the stationary phase and will ensure that the stationary phase stays stable as when it is coated onto your support or the backing that you are using. Then comes the process of coating the plates with the slurry that has been prepared. This involves pouring or immersing and spreading or spraying onto your support or backing plate, and then smoothing it over to get as uniform a thickness as possible. So you understand that this achieving a uniform thickness of that coating is important, and in fact spreaders are available that help to smooth it over and maintain uniform layer as possible. This also tells you why the commercially available plates may be convenient and a more standardized way of using a TLC plate. Then these glass plates are heated in an oven at high temperatures to activate the adsorbent. So the time again is standardized depending upon the mixture and the composition of the silica, but typically the adsorbent activation requires heating the plates after the slurry has been coated onto these plates. Once your sample has been applied and has been separated, the critical step is visualization. But prior to the visualization, what is a very important thing to remember is the sample application. Now remember that once your plate is ready for the sample to be applied, or you've taken out, say, a new plate from a set of plates that you ordered or made, remember that nothing should be allowed to contaminate the surface on which the separation is going to take place. So it is very critical that these plates not be touched with your hand. Amino acids from your fingers or lipids from your fingers may contaminate the surface on which the separation is to take place. So it's very important before sample application to have taken care of these things and to hold the plate in a manner that keeps the separation area free of any contamination. Some plates can be held with forceps, so alumina and plastic plates can be handled with forceps to prevent the contamination. Then, as far as the sample application is concerned, again, intuitively, the shape of the spot and the amount of the sample that will be applied will affect how well your analytes separate out. Again, intuitively, you understand that if a very large amount is applied and the surface area and length of the plate is restricted, then by the time the mobile phase has moved through your plate, you may not have, may have been too much, and there has been too much sample, then these spots will not resolve very discreetly. You may not get discrete spots. The separation process itself, apart from the sample application amount, it depends on the balance of the polarities. So the polarity of the plate, that is the stationary phase that you've coated on it, the development solvent that you're using, the mixture of solvents that are being used, and the spot material that is your mixture of analytes. That is also in a certain matrix, it has its own polarity. So ultimately the separation that you will get will depend on the balance of all these polarities. Now the point at which you stop the process, or the TLC process is stopped, is the point when the solvent in which your plate has been kept. Remember, the solvent is just a thin layer at the base in a tank, and that tank atmosphere is allowed to be, as we saw earlier, be saturated with your solvent and its vapors. And once the solvent, you can see the solvent has reached the top, or if you've been now doing this experiment for long enough, you usually know that it takes maybe 45 minutes or 90 minutes to happen, so that you can move around and not always have to keep watching your plate. So once the solvent has reached the top, the TLC plate is removed, then it is dried, and then comes the point at which the separated components of the mixture are visualized. Now, ideal situations and conditions for these are: the spot development itself should be done in chambers and in a uniform dust-free environment to help you visualize cleanly your analytes of interest. A lot of things affect the ultimate visualization, just as the separation itself. One is the vapor volume. So there are different methods by which visualization is done. It could be by dipping in your visualization solution, it could be by spraying, and it could be vapor phase contact. So we'll again reiterate this. So different conditions such as the volume of the vapor, the orientation and configuration of the chamber. So the chamber may be vertical, it may be horizontal. So companies develop different kind of chambers for different purposes, and typically, of course, the most common one is the ascending one, which is done vertically, but there is radial and horizontal development also under certain conditions. So these factors affect how the spot not only separates out, how the mixture and light separate out, but also how well the spot is visualized. Now this is an example. We had shown a schematic earlier, a typical TLC vertical chamber apparatus for separation, and we have been using this for, as I said, separation of the lipid components of high density lipoprotein. And so this is how, as you can see, the solvent has just about moved up to less than a third of the plate on which the separation will be taking place. The chamber has been sealed by a lid, and it's a typical glass tank in which the atmosphere is being saturated. Now again, the saturation, the point, what is important is also the humidity around in the room. So in more humid conditions, the saturation typically occurs faster. In drier conditions, it occurs slower, but it is a little more uniform. So all of these factors have to be kept in mind. If the same experiment is being repeated in different seasons, you may see different results depending upon not only the composition of your solvent, the mobile phase, but also these some of these atmospheric conditions. Now here are some examples. As we said, the most commonly used stationary phase is silica. Now, as we also earlier mentioned, depending upon the relative polarities of the stationary and mobile phases, this chromatography is called either normal phase chromatography or reverse phase chromatography. Now, silica by nature is very versatile, gives itself up for a variety of modifications. So, in a normal phase chromatography, the stationary phase, such as silica, is more polar than the mobile phase. Whereas in reverse phase chromatography, the stationary phase is less polar. So, silica itself is used in normal phase, and then if it's been, say, alkyl modified silicas, so specific silica, modified silica comes for your reverse phase TLC. So alkyl modified silicas, for example, are used for reverse phase TLC, and reverse phase TLC typically a little less environmentally hazardous, also has shown better resolution and more accuracy than sometimes, and for certain compounds, even normal phase chromatography. Now, we have listed here some examples. So, silica gels typically is used for separation of amino acid and hydrocarbons. Remember, we also used paper chromatography for silica gels. Then magnesium silicate stationary phases are often used for acetylated sugars, for steroids and essential oils. And then a specialized type of TLC in which silver ion is impregnated into the stationary phase is often used to check the purity to identify fatty acid methyl esters or triacyl glycerol components. Now, this is a really short list of examples of some stationary phases that are used for different compounds, a very wide range of stationary phases, and a wide range of chemical organic compounds are separated. Inorganics, as we said, are separated using TLC. Now, stationary phases are also available for racemic compounds and sometimes are used for separating enantiomers, such as for macrolide antibiotics, as a quality control procedure to check for the purity and to see the different compounds, say polyphenols, etc. So they are used not only for chemical compounds which are very distinctly separate, but they are also used for racemic compounds and enantiomers. Now, as we said, the stationary phase will be one of the critical criteria for determining the separation because of the knowledge of the nature of analyte you're trying to separate. But the mobile phase is also critical for the quality of separation that you will eventually achieve. So an ideal mobile phase should have all these properties, and as we said, the Prisma algorithm is often used to maximize and optimize the solvent strength and selectivity of the different solvents that will go in to make the final mobile phase. So the ideal mobile phase should not chemically affect or dissolve the stationary phase, which is understandable. It should not react with or cause chemical transformations of the separated compounds. If any chemical transformation is envisaged, as in when we derivatize a separated analytes for visualization, that should be done by the development agent uniformly for all the compounds. So the mobile phase itself should not be causing any chemical transformations of the separated compounds. Then ideally, because you're keeping the solvent in a tank and it is evaporating, the actual composition of the mobile phase changes. So no reuse ideally of the mobile phase, because this will affect the reproducibility. So if you're trying to check whether the separation had occurred optimally and you reuse the mobile phase, it may not give you the same results. Then the mobile phase should be easily eliminated from the adsorbent layer, because remember, your adsorbent layer has to be dried before the visualization or spot development process will be taking place. Then of course your mobile phase has to be compatible with your detection methods, and the conditions and the time of the preservation of the mobile phase solution will again affect resolution and reproducibility.